Welcome, my man. How you doing,
Thank you so
dude?
much, man. That's by far the best introduction someone has ever done to me.
Well,
Thank you so much.
I'm just mad that I didn't realize you also are a musician yourself, and so I'm excited to see the next time when you and I play together, and
Yes,
hopefully that can be in
yes,
person sometime.
yeah, it
So
would be
I
great.
know you got a lot to tell us. I know you got a lot to say, and I know that your internet is shaky. So in case you drop out, I'll just come back on here and sing a song about what you've said so far. If anybody has any questions for us while Marco is giving his presentation, feel free to throw them in the chat, and I'll jump on and I'll stop Marco and ask him for a little clarification on that. So I see you've shared your screen, Marco. I'm going to open that up and I'll give the floor over to you, my man.
Yes. So I guess my screen is live now.
Yeah.
So everything is set. Okay, great. So today I would like to share a little bit with you some experiences that my company has gone through in developing an open core platform for federated machine learning operations. So that's where this FLOPS acronym comes from. I'm currently a lead machine learning engineer at Scaleout Systems, and let me pitch my company a little bit to start with. I would like to start by sharing with you this concept of data gravity. So in the past decade or so, we have seen data set exploding within organization, not only in the industry, also the academia. And as data expands, we see more and more application gravitating towards data. What we believe at Scaleout, that in the enterprise data center of the future, we won't have, let's say, 10,000 servers in one location, but we will have a fewer servers across 10,000 different locations. And that's why we are a startup that focuses on decentralized machine learning. We were founded in 2018 in Uppsala. It's a university city which is 50 kilometers north of Stockholm. It's a beautiful place, so if you come to visit Stockholm, please come and visit us. It's a very nice one-day trip, I would say. But coming back to us, we are a team of experts in applied artificial intelligence and distributed computing. We have 5 PhDs in the company, which one is a full professor and 3 others are associate professor in Uppsala University. And combined together, we have over 100 peer-reviewed publications. So as you may have understood, we are a spin-off of a university research lab. So we started within the life sciences. We collaborate with AstraZeneca, Prosilico, and Research in the beginning, and Scilife Lab from the academic side. And now we have grown and we have more collaborations with other research organizations in Sweden. But we also have leads in the automotive and in the airline industry. And I will tell you a little bit more about use cases.
Uh-oh. Might have lost him right when it was getting good. So we'll just stand by while he reboots. And I see him again. Cool.
Yeah.
He's back.
Okay, so great. So I will just repeat about the outline. I will give you a gentle introduction to federated machine learning, why you should bother, and some case studies. And then I will talk a little bit about our open source platform for federated machine learning. I will tell you a little bit about the architecture and design choices. And then I will talk about our managed solution for federated machine learning, FLOps Studio, which builds on top of FEDn. And we will finish with some questions. So let's get into it. So what I've seen so far, the current in both in industry and a little bit in academia as well, is the following current best practice. You have your data mesh. You may have a little bit of data on the edge, a little bit on cloud, and a little bit in your enterprise. What you do is to run a data integration pipeline, which will consolidate this data and move it to a central store where your data scientists can access it. This could be a data lake, perhaps. And then you have your training process that is based on what your data scientists have decided by accessing this data, which access data centrally. And then finally, you're going to serve your model with Web2 APIs. And I would like to challenge this way of working. So there are basically three challenges that you may encounter. So first of all, if you're not a single organization, it might be that you want to collaborate with your competitors to generate some machine learning model that can give everyone some useful insight. But maybe you are not willing at sharing your private and proprietary data, because that brings great business value to your organization. And furthermore, it might be that you can, even if you wanted to share it, you may have customer data that you are not even allowed to share. You know, here in Europe, we have GDPR, but there are other regulations as well that prevents you from doing so. And finally, you may have this fog or edge use cases. So imagine having a fleet of car which is collecting road data. And this data is too big and too expensive to shuffle over the network. So it is hard to have it in a central store, and it gets cumbersome. So that's where federated machine learning comes into place. So there is a paradigm shift. Instead of having the data centrally and having a machine learning algorithm to look at it all at once, you can sort of having several machine learning agent algorithms that here are represented as client, which could access data locally. And in this way, the data remains private, and you can train some less accurate models on the edge. And then you can instead aggregate the models centrally. So you will send the model weights to the cloud. And then basically you will have an iterative process in which the model aggregation, latest and greatest model gets sent back to the clients, and you will iterate to get a better and better model. So in this way, your input privacy is preserved because only the clients can touch the data. There may still be concern on the output privacy because, as you know, from the weights, sometimes you can still get some meaningful information about the distribution the model was trained onto. But I will tell a little bit more about the output privacy, I think towards the end of the presentation. So it's a way that you can preserve it anyway. I would like to go a little bit more deep in how federated machine learning works so that you can understand a little bit better. And of course, there are many ways of doing this, but I will talk about federated averaging. I've seen many people using it in the academia and many organizations using it for industrial purposes. So in a nutshell, you have your central aggregator, which coordinates a number of training rounds. It will initialize the weights as it happens in many stochastic gradient descent algorithms. And for a predefined number of rounds, let's say n, you will run client updates in parallel. So let's say you have k clients. We have a for each loop here, and which will go in parallel and communicate with the distributed clients. And then you will pass the current weights to the clients. The clients will run a number of steps of stochastic gradient descent. So you can see it here in the client update. This is the same as what you are used with in deep learning, for example. And you will get the weight updates from each of your clients. And then you just take the average and update the weights and cycle through it. So the weights will be pushed back in the next rounds, and you will have a loss function and an accuracy graph such as this one that you can study. If you are interested in the bloody details, I link the paper here. You can go ahead, give it a look, or you can just Google federated averaging. This is just scratching on the surface what I'm showing to you here. There are many studies that show that this works in practice. Here I show an example from one of our use cases. I'm plotting the accuracy against the overall training steps. And this is a life science use case. So it's detection of acute myeloid leukemia. So it's a classification problem. So what we can see here is that with federated averaging, in the beginning we have a little bit of an instability, but if you look at this green line, in the end, the algorithm converges as good as the centralized global model. And we can see also that there is an improvement over what you get by training on site, on a single site only. So this is the best local model that you see in blue. And here even a small improvement, since we talk about detecting pathology in patients, it's good, it's desirable. So, but now you will say, but Marco, how is this different from distributed machine learning? Why can't we just use Spark or Autobots? Well, there are some important differences, and I will say right away that federated machine learning is not distributed machine learning. You could see it as a subset of distributed machine learning if you want. So there are two important differences. So first is that the data is heterogeneous in different sites where you're running your clients. So you may have a situation like this one. Of course, this is like just a simulation that we came up with, but just to show the purpose, the problem. The purpose of this is just to show the problem. So here we have cipher 10, and we say what happens if the clients have access on only 3 distinct classes, only 4 distinct classes, and so on. So we can see that if you access only 3 distinct classes, the accuracy is heavily affected. So your data scientists need to think about this when they make such a model in a federated way. And then the situation improves as the data gets more homogeneous. So your conversions may be affected. Challenge number 2, which is what we mostly focus on with FEDn, is the system heterogeneity. So you have scalability challenges. Some clients may be slower in sending you the update. And what do we do in this case? If we wait, some nodes may remain idle, so compute power not being used. And if we go async, then the global model may advance so fast that the clients' updates that come from the slower clients may only make the model worse. So this is a problem. And then you could have weak connection of certain sites. So like the network protocols that you may use in Spark or in Horvaths may not work as good in this situation. So I would like to talk, before I go into our products, I would like to talk about some use cases to convince you that this is something that you may want to use in reality. So I talked a little bit about medical image applications before, but we have a few use cases. Like we have more than one use case. And the business need, it's quite clear. So you have doctor annotated data. So it's not like me and you can annotate this data, and doctors are expensive and there are only a few within each organization. And you need a large amount of data to train these models to reach sufficient accuracy. So wouldn't it be nice to leverage multiple labs? So we can work together towards getting better and better models to aid doctors in doing this kind of diagnosis. So it might be that organizations don't want to share this because of business value, but here it gets even more serious because this is patient data. It's not like the organization doesn't want to share. There are regulations, and thank God there are, which don't allow for the data to even be shuffled over the internet. So this is a clear use cases in which federated machine learning will be needed. Another industry sector in which we work is air traffic management. So organizations such as Eurocontrol, for example, they operate airplanes basing on trajectories, and in order to make this process as smooth as possible, we want to have accurate trajectory predictions. So we may benefit from airlines collaborating into generate these central models for making predictions. But again, there is customer data which may or may not be used in order to do this. Even if they willing to share it, they cannot. And also, I will say that airlines are not keen in sharing their data because it's very, there is a lot of competition between the airlines, and the data it's very important in the business to properly advertise their flights and for other processes. So again, this is another use case in which we could shift to the federated paradigm. Use case number 3, and here I'm going in a little bit different direction, as usually, as far as I have seen, we have a single organization making these models. So we may want to do edge learning in self-driving vehicles. So we need to collect a huge amount of data to have accuracy for safety reason in these systems, and this large amount of data is really cumbersome to manage and to shuffle around. So here, even if it's not a regulatory problem, or even if there is no problem in sharing data between the organizations, so there is no business concern, it's extremely inefficient to shuffle all of this data. So again, why not to move the computation to the data instead? Okay, now I will move to the second part of my presentation. I will introduce to you our open source platform for federated machine learning. It comes with an Apache 2 license, and we design it with resilience and scalability in mind. You can use it with whatever machine learning framework you want, as long as you serial in a way that that we are happy with. And we have examples for Keras and PyTorch that you can look up, and even helpers for this. And it comes with a user-friendly UI. So I've seen a lot of clients and collaborators being happy about it. You can find it on GitHub, and if you want to dig into the science behind it, we have a paper published, and you can find the paper on the preprint on the archive. It's publicly available, no secret. So let me share a little bit about the architecture. The architecture is divided in 3 tiers. The first tier, we have the clients, which are the only entities that can access the data in order to preserve. We design it this way in order to preserve input privacy, as I told you previously. In the second tier, here we have something maybe a little bit different from what you may have seen from other frameworks. We have a system that is inspired to MapReduce. So instead of reducing the weights, aggregating the weights in a single step, we have this idea of a stateless load balancer and aggregator, which we call combiner, which basically acts as a load balancer. So instead of reducing everything at once, imagine having several 100,000 clients. You can do a first aggregation in the close to the clients, and then send fewer data to the reducer to aggregate, so that the reducer doesn't become a bottleneck. So this allows for better scalability. Finally, in the tier number 3, we have service discovery, which is used by the services to, discover the IPs and the domain names of each other. We have monitoring and model checkpointing and the APIs. So this architecture can be very flexible. So imagine I am okay, I will not mention any airlines. I think maybe we have NDAs. Let's say I am airline number 1, and I have all of my clients that are running in my internal network, with high bandwidth. And then I have airline number 2 with other clients running with their high bandwidth network. So if we place a combiner within the high bandwidth network, this combiner will be able to serve a lot of clients, basically, because there is no network concern. And we may have even more than one combiner within the same network, of course. But the idea is that we can aggregate the weights before we send it over the slow network to the reducer. So we do a first aggregation to make these heavy models smaller, so we send fewer data. But this, as I said, this can be simpler than this. So if we have high bandwidth between combiner and the reducer, and we don't have many clients, we may as well just deploy a single reducer and single combiner, and we can have everything within the same fast network. So it's completely up to the engineer that set this up. So it's flexible in this sense. And yes, we implemented this in Python. We support Python 3.8 and 3.9. Seems to be enough so far, because anyhow, the user can write code in whatever language she wants. We have a way of wrapping it. And we use language agnostic APIs. So for the base services that are here in gray, so monitoring, service discovery, and so on, we use a REST API. And for combiner, reducer, and client communication, we use gRPC streams, which proved to be quite robust, even over the public network. Yeah, so the reason why we want to be language agnostic is that we envision a future in which we may have lightweight clients, which may run on devices. So we may implement it in Rust or C, or even assembly, who knows. Yeah, so this is what we do for our customers. Okay, so let's get into the managed federated machine learning operation. So this is something that we are currently work on. Hopefully we're gonna have it in preview in the beginning of next year. We call it FLOps Studio. So it's a platform for managed federated learning operations. So our idea is to have an advanced alliance management. So we would like our users to be able to manage multiple FEDn alliances and projects with a single API and user interface. We will provide a system like advanced monitoring for system and model performance in all of the 3 tiers of FEDn for each of your project. And we will provide detection of malicious model updates, which may bring your model down. So yeah, imagine that you could have a client that maliciously sending random weights to the reducer or the combiner. This is, of course, bad. And also, we will do some user code scanning, yeah, in order to avoid this. Finally, we will have secure authentication for the UIs and token-based authentication for clients and combiners that our customer would like to plug into FLOps Studio. So coming to the MLOps, the life cycle it's quite similar, I will say, to what you see in centralized machine learning. There is only the first part that is a little bit different, so the training part and data collection part, and this we solve with FEDn. And basically what we aim to do, instead of reinventing the wheel, we would like to interface with the tool that you already love and you are using in your organization. So MLflow, Kubeflow, Azure Machine Learning, Amazon SageMaker. So you don't have to move everything, but you can keep working into your platform of choice. Now something a little bit more advanced. I could have a whole presentation about this, but I have condensed everything in a slide, so bear with me. So how do we protect output privacy? So we want to upload these weights to a cloud provider in a way that the cloud provider cannot access the weight. How do we do that? So there are, of course, many ways of doing this, but what we are looking into is trusted execution environment, and in particular into Intel SGX. So the idea is that these TE environments provide a mechanism to preserve data and code confidentiality and integrity when you're running on a third party, so when you run on cloud. So that's the idea. So these Intel processors, they provide an enclave within the hardware, which is protected processor memory, which cannot be accessed by the hypervisor or by the operating system, or even by the apps that you're running on the virtual on top of the hypervisor. And so if any of these get compromised, the attacks can only go up in the stack. They can never reach the enclave. And even the cloud provider will not be able to look into it. So the idea is that if we run tier 2 and 3 inside this enclave, the output privacy will be somewhat preserved. All right, this concludes my presentation. I hope this was interesting, and I hope I didn't drop. I'm still online.
You are still here with us. That is so cool, man. I'm very happy to see what y'all have done and how you've done it. There is probably, I imagine people have questions, so feel free to throw them in the chat while we're waiting for that to happen, because there's a little bit of a delay on the stream versus when we hear it. And there he goes, just in time to take off. But he's back. All right,
Okay, so how much of it did you see?
I saw everything. I was just chatting about how there's probably a delay in the
Oh,
chat.
okay.
And I encourage people to ask questions. I am really interested about that slide that you showed on how, in your mind, MLOps and FLOps, the flops, differ. And you talk about it's mainly at that beginning, like the data acquisition piece, and then it goes into something that we're more used to seeing. Can you go and break that down a little bit more? And does it matter? Like, I feel like what you were talking about, where the different types of data probably play a big difference in how that looks too. So can you go a little deeper on that?
So, of course, it becomes more challenging for the data scientists, right? So there must be, in the beginning, a research phase in which we anonymize a part of the data so that the data scientists can collaborate and access it centrally and do some standardization. So this is crucial. So if we have cars, this data is highly standardized. It comes from sensors. So there might be a little bit less of a problem. You may have sensors that work differently on different companies. But it becomes a problem when you work with microscopes, for example, for the assisted pathology. So you must anonymize some data so that you understand. So if in this research lab, the hue of the microscope differs from the one that I get from this research lab, the data scientists need to know, otherwise the model will not converge. So automating all of that part, unfortunately, we are still far from it. So that's crucial, and that's what will be different in the beginning. Once this is standardized, you can install the FEDn clients on site, and everything is automated. And what we envision is that the FEDn will integrate with, let's say, Azure Machine Learning, and will start to log data and register model on Azure ML, for example. So this is where I would say we will have something a little bit different. And then you can measure data drift as you do it usually, but you're going to have different sites, and you're going to have to be mindful of what measure of data drift you are sending centrally so that input privacy is somewhat preserved.
Yeah, completely. And a lot of times we do hear federated learning being something that is touted to be the best way to counter the privacy problem, especially when it comes to Europe and GDPR and all that good stuff, and even like the new proposed regulations that you have on that. When do you feel like federated learning is not the answer?
So I will say, so like if you don't have any of the challenges that I've been talking about, of course, don't bother. If we have one of these challenges and you don't manage to have an agreement, there is no way of anonymize a small amount of data that gives a scientist. Data science. Sorry, I'm back.
Yep.
So it wouldn't be the answer. So the situation in which you cannot experiment with federated learning is the situation in which you cannot send a little bit of data centrally so that you can standardize the problem. Or if you have a problem that it's impossible to standardize. So that's when you cannot use it.
Interesting. And so
sorry.
when you're talking about standardizing, this also came to my mind. You mentioned how like this example of the microscope, and depending on which microscope you're getting the data from, it could be different, and that could be because you don't have standards in place. And until you get those standards, you're not going to, like, you have to do it manually. Do you see the standards coming from microscope producers, from just the data scientists that are mandating down standards? How do you look at those standards being put into place?
So actually, this is a very, very interesting question because I think for lab equipment, it depends on the way the lab equipment is calibrated as well. So I don't think they will manage to standardize it, but like you can share, we were able to share enough data with the data scientists so that you can come with some solutions. So for example, you can run cycle GAN, so which translate all of the distribution to a single distribution before you do the training. And so you have some sort of, artificial way of standardizing the input data. Yes. Maybe for sensors, like their calibration, like at least for what I've seen, maybe it's less. Okay, for the use cases that I've seen, it should be less of a problem. But maybe there as well, you could have certain cases in which like calibration may affect the result. Yes.
Nice. All right, last one for you.
You have some fleet that never, like, let's say you're trying to do anomaly detection. You have some fleet that never fails. So, then you cannot detect the failure.
Yeah, it's very hard to figure that out. And it reminds me of a conversation that we had for the podcast with this great guy Curtis, who was talking about how some of these problems, like that he was working on, he was trying to predict bad data when you can't find bad data. Basically, like one example that he used was how many times you say, "Hey Alexa," but Alexa doesn't actually respond. And so he's trying to predict that amount of bad data that you're getting just through the statistical distributions of the data, and saying, all right, well, we never actually know for sure, but we can kind of figure it out. And so we can say these things. It's nice to think about that. And I'm glad I'm not the one that is having to figure it out, because it's some seriously complex stuff.
Yes.
Now, last question for you before we jump. What gets you the most excited about federated learning as you look forward?
So for me, I see that like there is a little bit of competition, but the competition is not so much. So I'm in a startup, so what gets me excited is that we may get this right, maybe the one getting this right, and making a tool that a lot of people will enjoy to use. So that gets me really excited. And also I'm seeing a lot of interesting alternative approaches coming out. There is, we have been focusing mostly on federated average, but there are some research labs that we collaborate with that are doing very cool stuff, and I'm looking forward to implement these approaches.
Excellent. Well, dude, I think that is it. I want to say thank you. This has been awesome. I learned all about the flops, or the federated learning ops, as we could call it. And for everyone that is listening, if you would like to continue chatting with people that are here with us right now, that have just been in the meetup and the chat, you can go over to the left sidebar in the gradual instance that you're on, basically the platform that you're watching this on. If you're not on YouTube watching it with the DPhi people, if you're on the MLOps.Community platform, you can go to the left sidebar, and there is a section that says match, And so if you hit that, you can get started and you will match with another random person that is watching this with you. And so it's a great way to network. That is it for today. Marco, man, thank you again. I really appreciate this presentation, and we'll see you soon. If anyone has any questions for Marco, please reach out to him. You're on LinkedIn. What are the best ways to get a hold of you, I guess, Marco?
I would say LinkedIn is the best. Yes, please connect with me and ask as many questions as you want. And we also have a Discord community. So if you search for Scaleout Systems, we will find it on Google. So
Nice.
you can join there as well.
That's it. Y'all heard him. Scaleout Systems. That's what we've got for today. Thanks again, Marco. We'll see y'all later, and enjoy the rest of your day. I'll see you in the one-on-one random networking matches if you want to do that right now. Bye, everybody.
Bye-bye.